Hello, everyone. I'm Jiajun. I'm a new assistant professor at Stanford University and excited to be here and to talk about my research. My research is, the title of the talk is Learning to See the Physical World. So humans live in the physical world. As humans, we effortlessly see the world, navigate in the world, and interact with the objects in the physical world. So as AI researchers, we want to build AI and machines that can replicate such abilities. So to do that, let's first look at what humans can do. But in the case of a very simple game, the popular game, that is the game of Jenga. And this is a 6-month-old baby playing the game of Jenga. Looking at what the baby is doing, she's able to play the game in a different way. Although not playing the game the way that we expect, you can see from this video that this 6-month-old baby has an amazing ability to recognize what's in the scene, to pick up objects, segment objects, find the blocks, pick up the blocks, interact with it. And this is the theme of my research. And so that's why I sometimes call it the infant machine. That is, can we build a machine that learn and behave like an infant for any new objects, including objects we've seen like blocks, but for a young child, and we have never seen objects like this. So for any new objects, including those we have never seen before, can we recognize its shape, geometry, and physics, predicting how it will behave if we interact with it, and to actually interact with it? So this is the theme of my research. So how to do that? Well, of course, we can try to use now this very popular deep networks, and you can see, in scenes like this, the networks does really well in segmenting objects like cars and roads. On the other hand, such kind of approach, if we directly try to scale it up, to not only recognize objects like cars, but also to unseen objects, to object geometry, to object physics, then we have a challenge, because by relying on data, how can we really scale it up to collect annotations that are beyond object semantics like cars? Now, if we want to annotate the geometry of the object, if we want to annotate the physical properties of the object, that just seems very hard and it's almost impossible to collect such annotations to train the deep networks. So the alternative approach is we can try to think about we're living in this physical world, then there's physics governing us, and so what's the physical model behind it? For an image like this with a few blocks, we understand that there is underlying physical states, which includes object geometry, physics, intrinsics, there are extrinsics like positions, and scene descriptors like lightings and camera parameters. And our goal here is, how can we really turn these states like object intrinsics and extrinsics into images? And this is the physical model behind what we see. And it's an important subject in computer graphics called rendering. Beyond a single frame, you can do that for multiple frames. Across the frames, there is dynamics for it. Condition on the current state, condition on actions, and what's going to happen in the future. In a video like this, the actions you can see is, you can assume it's like gravity. Right, so this kind of modeling approach is trying to understand what's the physical model behind the physical world, and to use it for us to understand the scenes, for scene understanding. But such a model also has other challenges. For example, the biggest challenge is probably once we have this top-down model. Now, when we understand object geometry and physics, we can imagine how the scene will look like. But if we want to solve a bottom-up inference problem, if we're not given the scenes, how can we really infer the geometries? Right? This is an unsolved problem, and traditional approaches like sampling and CMC is very too slow to be practically useful. And second, models are always approximate, so they're not good enough to capture every details of the world. So the theme of my research, or the philosophy behind my research, is to integrate the two, to combine learning with modeling, so that you get the power of both the data and the model. And concretely, we have two themes of research. One is learning to invert. That is, as we said, how can we really use top-down models for bottom-up inference? And our solution is to learning to use it, to learn to invert the physical model, but take the intermediate representations or take the target from the physical model as our training target, as our intermediate representations of training. The other is learning to augment. As we said, models are only approximate, not capturing the details in the world, maybe too deterministic. So can we use learning to augment it to make it more accurate, more efficient, to able to handle uncertainties? So putting them together, the key principles behind my research is to build physical models for these physical worlds, and to think about what the model doesn't give us and see if we can use learning to help us to solve the problem. Thank you very much.